Okay, so we're going to finish off the story of the discovery of the atom. Remember, so far we know that we kind of have a working model for the atom, right? And it all ultimately emerged from, or at least we like to attribute the beginning of our understanding of the atom to Becquerel's work when he discovered radioactivity in 1896, which was, as he defined it carefully, the spontaneous emission of energy from a material. As soon as this was discovered, and for several decades after, there was great excitement in scientists who were trying to identify new radioactive materials and then use those to try and understand more of what is going on inside the atom itself. So one of the realms of investigation that became really important after the atom was first really defined, after the Rutherford Bohr model came out and became accepted reasonably well, was this notion of what can we find out by altering the atom? Can we mess with the nucleus and learn something because we're doing experiments with it? And this is the field of experimentation called artificial radioactivity, where you force an atom's nucleus to become unstable by propelling subatomic particles at it. So we'll look at one of the earliest examples of artificial radioactivity, which was, as many things were, first done by Rutherford. He took nitrogen atoms and he sent alpha particles, helium nuclei, at them, and they would make, and we can test our predictive abilities to see if everyone is still functioning on nuclear reactions. It should make something with 9 protons, and if you look at the periodic table, that's fluorine, and it's going to weigh 18 mass units, right? But it turns out that fluorine-18 is not stable, and it's not stable with a pretty short half-life, and it undergoes decay and ultimately forms, by in this case tossing a proton out, and ultimately forms oxygen-17. And this is one window into atoms to find out what destabilizes them, what doesn't destabilize them, and what can we learn from that process. But one of the issues is that in order to get any kind of subatomic particle into a nucleus, if the only ones we have to work with are ones that are charged, right? We have alpha particles, right? They're kind of big, they're highly charged, they're slow moving, for instance. And getting something with a 2+ charge into a nucleus that is positively charged when it's not moving very fast is pretty tough to do, right? So these are not easy to inject into nuclei. And so the whole artificial radioactivity, the notion of bombarding nuclei with charged particles, was pretty tough to do, right? You could only really bombard small atoms like nitrogen with these. Anything with a higher nuclear charge, you're just going to propel that. You're going to propel that alpha particle away. You're not going to learn anything from it. One of the scientists who was thinking hard about how to speed up those particles so that they could, in fact, penetrate the nucleus of more highly charged or larger atoms was James Chadwick. He's the one who discovered the neutron in 1932. Now, he was trying to come up with clever ways to do this and more experimental approaches, that required considerably more power to be able to propel these charged particles into nuclei. Rutherford was reticent to get involved in this kind of a game. He liked really simple, nicely, cleanly designed experiments, and so he actually hesitated going down this route much farther than he already had at that stage. And so this is the notion of particle acceleration, and trying to figure out how to accelerate particles enough to be able to penetrate larger nuclei kind of stalled out a little bit in physics in this early 1900 window, because as Chadwick calculated, and this is a slightly more mature picture of Chadwick after the last one, you need about 1 million electron volts in order to get a charged particle into a larger nucleus. Now, an electron volt, the details of an electron volt aren't that important, but the bottom line is an electron volt is an absolutely small amount of energy, but 1 million electron volts is not so small. And being able to propel or accelerate a particle with 1 million electron volts is non-trivial. So the one who tackled this issue of how to accelerate alpha particles or protons or any other kind of charged particle and to get them into another nucleus was Ernest Lawrence. Ernest Lawrence was an American scientist who worked at Berkeley. He was working in the late 1920s at this time. He tackled this problem with considerable enthusiasm because he was quite the experimentalist. He loved building large, sophisticated instrumentation. And as you'll see, his progress in this field of particle acceleration is really remarkable in an incredibly short period.
He and Rutherford are pretty much different kinds of animals.
Different birds,
and experiments. Okay.
Exactly, very different. The problem is that to get 1 million electron volts, you need a big power supply. And that's just not that feasible for these guys to do, at least certainly at the time. And so Lawrence was trying to find a way around this sort of brute force approach to accelerating particles. And he was trying to find a clever way to harness energy in order to speed up these particles. And so he had this problem kind of in the back of his mind. He was reading through the scientific journals. He found a paper by a German scientist, Widerøe, that was called On a New Principle for the Production of Higher Voltages. And it was in German. Lawrence didn't read German, but he looked at pictures and he could get the gist of it, and he's a sharp guy, right? So he ultimately got the gist of what Widerøe was suggesting and made his own notes, of course, and we still have copies of Lawrence's notes, which is really interesting. And effectively what he designed was a linear accelerator, which you've probably heard of. Well, you've certainly heard of, but other people have heard of. So he mounted 2 metal cylinders in a line, and he attached them to a voltage source, and he sucked all the air out, so he had a vacuum system. Okay, so there's a cylinder without anything in it except, well, nothing in it. It's a vacuum, right? And he sends a proton, which is positively charged, into one end of it. And what he does is he sets, rather than just trying to send a huge voltage across it to try and speed up this particle, what he does is he alternates the current on the voltage so that it goes from a positive to a negative to a positive to a negative charge. So when the proton first comes into the system, it's positively charged, and he's got the first cylinder set up to be negative. So that's going to attract that positive particle, which is going to accelerate toward it. And then right when that particle approaches the cylinder, he flips the sign of the voltage. It goes to a negative, it goes to a positive, and that proton now is completely repulsed, doesn't want to be there, and it heads out the other side faster than it came in. Right. So it's kind of a push me, pull you kind of approach, right? So we're attracting the protons in with a negative charge, we're flipping the voltage on them, and then we're pushing them out by sending a repulsive charge. And then the same thing would happen down the next cylinder, and the same thing down the next cylinder. And this way, you could take a relatively small amount of energy, and you could multiply it and speed up this particle with progressive pulls and pushes down this cylinder. But that's also going to take a lot of space. Right? You got to have a pretty long tube set up in order to propel these particles down it. And so Lawrence proposed, well, let's just put a curve to this tube. But in order to get charged particles to curve, you have to expose them to a magnetic field. So he stuck a magnet above and below this curved tube. So the tube has the alternating current, push me, pull you approach to speed up the particle, but he's keeping it all contained and keeping the particle turning because it's stuck within a magnetic field. Here's his first design, actually a patented cyclotron diagram. He named it the cyclotron as opposed to a linear accelerator because it's in a sphere. And the 2 pieces that are going to have the alternating current go across them are called the Ds because they're shaped like Ds. You can see one is the top half of this diagram and one is the bottom half of this diagram. And the particle goes between these, getting pulled into one side and pushed out to the other side under the influence of this magnetic field. So I'll show you a slightly better drawing of this here. You can see the Ds are in yellow in the middle of the diagram. You send the particle starts in the center and it goes through progressively larger spirals and then gets flung out towards the target when it leaves the magnetic field so it can go in a straight line. Pretty clever, very sophisticated design.